We're continuing with Chapter 6, which is on applications of integration. In this video, we're going to go through Section 6.2, which is on volumes. So we started where we developed the infinite sum tool, the integration process, to find just a general area under a curve. Then in the previous section, we looked at using this infinite sum tool to find areas between curves. And so now in this section, in Section 6.2, this is the first time we're going to venture off from using the infinite sum tool to find some kind of an area. Because remember, this infinite sum tool, this integration process, it's not restricted to areas at all, even though we developed it from that perspective. All right, so it says, in trying to find the volume of a solid, we face the same type of problem as in finding areas. We have an intuitive idea of what volume means, but we want to make this idea precise by using calculus to give an exact definition of volume. Yeah, and so, one thing to point out is that what they're saying here, so like when it comes to area, we use the integration process to find areas, but integration has also been used to define what area means. So which is kind of weird to think about, but, before integration, there was no, we had no way of finding the area under this curve, finding this area. So we could find areas of certain shapes. But the idea is if you're going to define what area means, then you want to draw the most general area possible, right? Like this is not even the most general. You would draw some area like this, and the definition of area would be based on what this area is, because that definition would include a square and a triangle. Okay, so that's the reason integration was invented, because we had no way of calculating general areas. And so that's what they're saying here. We're about to develop an exact definition of volume in the same way that integration was used to develop an exact definition of area. Okay, so it says, we start with a simple type of solid called a cylinder, or more precisely, a right cylinder. As illustrated in Figure 1a, a cylinder is bounded by a plane region B1 called the base and a congruent region B2 in a parallel plane. Okay, so we're starting with what's called a cylinder, or more precisely, a right cylinder. And when you think about the term cylinder, you think about this. But this is a certain type of cylinder. This is a circular cylinder. The general term for cylinder is you could have the heads of the cylinder could be any shape, but the heads are going to be a plane. It's going to be planar. Okay, so you've got the two base planes, and then the cylinder consists of all points on line segments that are perpendicular to the base and join B1 to B2. Okay, so this is a solid here. It's not just like a surface, with a hollow interior. This is like a full solid, and you've got these two base planes here that are separated in parallel, and then the cylinder is all points that are on line segments that are perpendicular to the base planes and connect the two base planes. That's the definition of the cylinder. And the idea is the base planes can have any planar shape. So this is a circular cylinder, and it's a rectangular cylinder. It's a rectangular parallel pipehead. And the volume of any cylinder is the area of the base shape times the height of the cylinder. And so for the circular cylinder, that would be, you do pi r squared times h. Here would be length times width times height. Okay, and so with this definition of a cylinder, we don't need to develop any additional integration techniques to find these volumes, to find the volume of a right cylinder, because all we need to do is calculate the area of the base, whatever it is, and we know how to find any kind of area now. So once you've so obviously here pi r squared and here length times width, but here you would use integration. So so here you don't need integration, right? For these are basic geometric shapes of the bases. But here you would need integration. You get the area of either one of the bases, but then you just multiply that area by h and you've got the volume. All right, but what about solids that aren't cylinders? So for a solid S that isn't a cylinder, we first cut the solid into pieces and approximate each piece by a cylinder. We estimate the volume of S by adding the volumes of the cylinders. So that's why they wanted to start by defining a cylinder. Because what we're going to do is, to get the volume of a general solid, we're going to break up that solid into pieces, and these pieces are going to be cylinders, right cylinders. And this brings me to an important point that I want to make. So, I've mentioned before that as we go through these applications of integration sections, we're trying to get an intuitive feel for how the infinite sum tool works, so that we can apply it not just for the applications that the textbook gives us, but even a general application that we come across. And so we want to be able to have a raw application that the integration formula hasn't been developed, and potentially develop that integration formula ourselves. That's one of the main goals of this course, that you have this skill when you're done with this course. So, okay, if you come across something where you're trying to solve for a quantity, the first idea is you're going to think about, and as you can see, this could be anything. It might not be an area or a volume. There's all kinds of different potential applications, but the idea is there's going to be some quantity you're trying to solve for, and you're going to think to yourself, can I solve for this quantity by breaking up the quantity into pieces and then summing those pieces? Okay, like here, for example, we're trying to come up with an integral for finding the volume of a general solid, and you think, okay, can I break up a general solid into pieces and then sum all of those pieces to get the total volume of the solid? And so what I want to point out here is that these pieces are going to be the same type as what you're trying to solve for, okay? What I mean by that is, so like we're trying to solve for the volume of a general solid, the volume. So the pieces, the individual pieces are going to be little volumes, right? Before this, we were solving for areas. So the individual pieces that we broke it up into were little areas, and we were adding up those areas. Here it's little volumes. We're going to be adding up the volumes. So remember that's important. If you're trying to solve for the total work, we're going to see how you can do that in a couple of sections. The work, like as far as energy, well, then you're going to be breaking it up into little pieces of work, and you're adding up all of those work pieces, okay? And so the idea is, here's a general volume, right? They make it as general as possible. There's no symmetry or anything. And the method is that we look at this and say, okay, I think we could solve this problem. We're trying to find this volume. We could break up this volume into a certain number of pieces and then add up those pieces. Okay, and so what we're going to do is we're going to break the pieces we're going to break this up into are going to be volumes, but specifically we're going to break it up into cylinders, right cylinders. That's the theory right now. Right? And this is the kind of the process you would go through from scratch on your own. And this is like a proposal. We don't know if it's going to work yet. The idea is, okay, we can break this up into little volumes and add up the volumes. And then specifically, though, these little volumes are going to be right cylinders. Okay, so how are they going to be right cylinders? The idea is we're going to put this piece on top of the x-axis. The x-axis is going to be the independent variable. I mean, it doesn't have to be the x-axis. It's whatever. We're going to put this piece on top of the independent variable axis, okay? The independent variable. And then we're going to break up that independent variable into a certain number of pieces, and then the endpoints of this interval along the independent variable is just the back and the front end of the solid. All right, now the width of each piece is going to be the height of the right cylinder. Okay, now I just want to point this out that like for whatever the particular application is, the width of the pieces can be anything you want. Like there's no requirement whatsoever on what the width, the delta x is, or the delta independent variable represents. There's no requirement on anything. The only requirement is that when you multiply the delta x or the delta independent variable by some value of the function evaluated at a point within that interval of the independent variable, the dimensions you get, the result you get is of the same units as what you're trying to solve for. So when we multiply, we're going to have delta x's that are going to represent the thickness of the height of the right cylinder piece. Okay, well then we're going to be multiplying it by some function of x, and that function of x is going to have to be an area, some kind of an area, because that's what's going to give us the volume, right? The f of x times the delta x is going to give us the volume of this piece, okay? But we're going to see that like the delta x can represent, it doesn't have to, the delta x doesn't have to represent the thickness. It can represent anything you want. You can set it up whatever way you want. But what's going to happen is you're going to have to check that the element you set up, the small piece you set up, you're going to have to verify in the end that, okay, when I make these number of pieces large, is it converging to the value that I'm looking for, or isn't it? That's going to be the final check. And so, okay, but just here, the delta x's or the height of the right cylinder, and then the function here, the function of x is going to give us the area of what? The area of, so you take a plane that's perpendicular to the independent variable axis, and that plane cuts through the solid. And so that's going to create a cross-sectional area. The function evaluated at x is going to be the area of that cross-section. And so you can see that the function of x is gets the area of the cross-section times delta x, that's the volume of a right cylinder at that x point. Okay, now you might be wondering, well, wait a minute, how do you orient the solid on the independent variable axis? It doesn't matter. However you want. I guess my answer to that would be whatever makes it the easiest for you and the most accurate, to where it's oriented a certain way to where at each x point you have a plane like this that's perpendicular to the x-axis that cuts through the solid, and to where you could get that function for that cross-section. So it doesn't matter what the orientation is. But yeah, depending on the orientation, if you turn this a little bit or to the left or the right, then the a of x at each x point with it from A to B is going to be different. Okay? And so, the next thing they do is they make like a visual, they draw a visual of each of these elements. And so the area of the cross-section you can evaluate at any point within each interval, the left endpoint, the right endpoint, because the area of the cross-section is going to be slightly different depending on if you do if you evaluate that area based on a plane that's cutting through at the left endpoint, the right endpoint, the midpoint, etc. But we're going to put xi star here to indicate you can pick whatever point you want. But if you're doing an approximation, then you want to do the midpoint. Okay, but here's one of the elements. Okay, you've got they put you can see the area is evaluated at any point within the interval, so that the plane that cuts through the solid, it's a flat, a purely flat one-dimensional or two-dimensional plane, is at any point within the interval evaluated, that area times delta x. So that's this volume of this right cylinder. That's this piece. Okay, so now you've got your element defined. That you've theorized that, okay, I think I can, to solve for this quantity, this volume of this entire solid, I can break this solid up into pieces. And here's the definition of the piece in this case. So now they do an example of 1, 2, 3, 4, 5, 6, 7 pieces, and just they take a look, and it seems like it's a good idea, right? It just looking at this, it looks like it's kind of coming into the shape of this. So okay, looks like this looks good. But then they don't show it here, but really the next thing you would do is, they'll show it in these next examples, is you would then do another one of these, but with like as many pieces as you can within reason. So maybe like 20, 25, 30 pieces, something like that. So like if we come here, you see they start off with 1, 2, 3, 5 pieces, then they go to 10, then they go to 20. And the idea is you want to, once you start increasing to like a decent amount of pieces, it should clearly be converging to what you're looking for. This is converging to a sphere. And you'll see examples where, you create an element and you think this should work, this element should work, but whenever you increase it to like 20, 30 pieces, it's clearly not converging, right? It's clearly not approaching the shape you're looking for. But if you go to like 20, 30 or more pieces, then it would be clearly converging to what you're looking for. Okay, so if we come back here, when you see that it's clearly converging, that the element that you've defined, as you increase the number of those elements that is clearly converging, that's when you can say, okay, I can make this into an integral. And so, all right, here's the volume of a piece, of just one piece. So it's the area evaluated at xi star times delta x, okay? And so then they write the Riemann sum here. So the volume is approximately equal to the sum from I is equal to 1 to n of the sum of these pieces, right? And if you were actually going to actually go through an approximation, it's a good idea to change this xi star to the x at the midpoint, as we know. Okay, but then, so they say here the approximation appears to become better and better as n approaches infinity. Okay, so now it says this approximation appears to become better and better as n approaches infinity. Okay, so yeah, so that's like, they kind of do this here. You can imagine they took that approximation to like, 30 pieces and saw that it's clearly converging. And so it says, okay, therefore we can define the volume as the limit of these sums as n goes to infinity, because we just did this. They just did this for as general of a volume as you could possibly get, right? Like, we're trying to make the definition for volume here. So there's no solid that you could come up with that's going to be more complex than this. So they say that you can define the volume for any solid, no matter what it is, as you can break up that solid into right cylinder pieces, and the challenge would be that function for the area is making sure that function is correct. That's the challenge. If you have some crazy geometry, then the challenge is going to be the area function. But if you can get those area functions correct, then the definition of volume is it's the limit as n approaches infinity of this here, which is an integral. So writing that in integral notation, so okay, here we go. Here's the definition of volume. So let S be a solid that lies between the tail and head of the solid, or between x is equal to a and x is equal to b, if the cross-sectional area of S in the plane P through X and perpendicular to the x-axis, it has to be perpendicular to the independent variable axis, is a of x, where a is a continuous function, then the volume of S is, so the limit as n approaches infinity of this Riemann sum. All right, so we can convert this to an integral. This infinite sum here converts to the S, this elongated S symbol. You put the limits of integration. You put the function. Just you don't have to worry about xi star or anything. Just put the function. Delta x becomes infinitesimally small, dx. There you go. Okay, it says, notice that for a cylinder, the cross-sectional area is constant. It's the same for all x. So the definition of volume just gives, it's a times b minus a times the height, the area of the base times the height. And this agrees with the formula for a right cylinder, the volume of a right cylinder, V is equal to a times h. Okay, cool. So now we're going to go through the examples that they show, and they're going to show different types of problems. So like, these problems are going to have different approaches to using the volume formula. That's what you're going to see. However, just notice that, yes, the approach to using the volume formula is different for each of these problems, but it's still the exact same concept in that we're trying to find the volume of something, and all we're doing is just coming up with a formula for the right cylinder volume piece, the differential piece. That's what's the same with every one of these example problems. We're always coming up with a formula that represents a piece of the solid that's a right cylinder, and then integrating that, because it's been proven here that if we can break down a problem where we're trying to find a volume of something to where we're breaking that volume up into pieces of right cylinders with the cross-sectional area defined at each x value, then we know that just take that as an integral. Take the limit as n goes to infinity of that. Okay, so it says, example 1, show that the volume of a sphere of radius r is 4/3 pi r cubed. Okay, if we place the sphere so that its center is at the origin, then the plane P of x intersects the sphere in a circle whose radius is, okay, so if we come here, so the idea is we have the sphere centered at the origin, okay, and we're going to walk along the x-axis, and so based on the definition of volume, what you're looking for is you want a formula that represents at each point on the x-axis, so you you have a plane that's perpendicular to the x-axis that cuts through the sphere. What's that cross-sectional area? Okay, and so what they're saying is that r here is the radius of the sphere, not the radius of the cross-sectional circle, the radius of the sphere. So by the Pythagorean theorem, you can get the radius y is r squared minus the square root of r squared minus x squared. Okay, and so with that, you do pi times y squared, and there's your a of x. And this works for any point from minus r to r, from any x from minus r to r. And so, okay, so you multiply a as a function of x times delta x, and there's your differential right cylinder volume, right? That's we have a formula for each of these differential volumes here, right cylinder volumes, for any point within the sphere. So that's the definition that we just developed for volume. So now just integrate that from minus r to r. And they do the integration, they get 4/3 pi r cubed. And they just show here, they increase the number of these elements, and you can see how it's, as you increase the number of elements, it's converging to the actual volume. All right, next example, it says, find the volume of the solid obtained by rotating about the x-axis, the region under the curve y is equal to the square root of x from 0 to 1. Illustrate the definition of volume by sketching a typical approximating cylinder. Okay. So here, they're saying find the volume of the solid that's represented by, so you take this area here and rotate it about the x-axis. Okay, so now this is a little different than the sphere. So is this a different type of integral? Well, no, it's the exact same procedure. All we want to do is find the differential volume. So like the volume of one of the pieces. So it's a right cylinder. All right, so if we think about this shape rotated, then what would be the cross-sectional area then of this? Here's the shape. What would be a cross-sectional area of this? Well, it would be, this is like a radius, it would be pi times this function value squared. That's the a of x for any cross-section from 0 to 1. So it's going to be that a of x times delta x. And so here it is as an integral. Pi r squared is pi x, and so that's the integral. You see, so it's all about just for the general volume formula. It's all about you want to find the a of x, the area of the cross section as a function of x, and that's what I meant by for each of these problems. The approach is different, right? So it's like this setup and approach to this was different than this revolving revolving that region around the x-axis, but it's still the same concept as far as you're just integrating that cross-section formula dx. That's the differential volume you're trying to find. That cross-sectional area formula times delta x. That's the individual element. All right, and so that's the general idea that they're going to do in the rest of these examples. So here, it's the volume created by rotating this area around the y-axis, and it makes sense here to have y be the independent variable. So to break this up into pieces based on delta y. Okay, here they want the volume obtained by rotating this around the x-axis, this area, and so this is going to have a hollow center like this, but here, like this washer-looking piece, that's going to be the differential element. It's still a right cylinder, but it just has it has a hole in the middle. You know, so what's the cross-sectional area of this? It's pi r outer squared minus r inner squared. So that's all you're going to do. The differential element will be pi times x squared minus x squared squared. So pi x squared minus x to the fourth, and then dx, and that's it. You're breaking this area up into those pieces. Like that integral, pi x squared minus x to the fourth squared dx, that's the differential piece. You know, that works. That's like a right cylinder piece. And so you sum those all the way from 0 to 1, and you get the volume obtained by rotating this area about the x-axis. So we're going to work examples similar to all of those shown here in the next video. So, you know, it's the same process here. They've changed it up a little bit. It's the rotating this area about y is equal to 2, right? The center is y is equal to 2. It's just you're going to have to set up the formula for the function of the a of x, and then multiply by dx. That formula for the a of x is just going to be a little bit different, but it's the same exact process. Okay, so it says the solids in examples 1 to 5 are called solids of revolution because they are obtained by revolving a region about a line. In general, we calculate the volume of a solid of revolution by using the basic defining formula. Yeah, I mean, if you look at these formulas here that they just associated with the solid of revolution, this is the exact same formula as for the general area of a general solid, not even a solid of revolution. So I don't even know why they said this, right? Look at this. This is v is equal to from the integral from a to b of a of x dx. Let's come back. Definition of volume. V is equal to the definite integral from a to b ax dx. This has nothing to do with a solid of revolution. And so that's what I'm saying. Solid of revolution or not, it's the same process is that you need to define what a of x is, or a of the independent variable is, multiply that by delta x, and you've got the formula for the volume of each individual piece, the volume of the right cylinder piece. And that's what you're going to be integrating over the entire volume. Okay, here's another example. It's just another variation. It's that same area from 2 examples ago, but you're going to rotate it about the x-axis. So we're going to work all kinds of examples like this, but it's the same process. With this, you can easily get the formula for, as a function of x, for this ring here, the area of this ring here, for any position along the y-axis. So with that, multiply that times delta x, and that's your differential piece, your differential right cylinder volume, then just integrate it. Okay, so now it says, let's look at some examples of solids that are not solids of revolution. You know, they say that, but I would say that example 1, the sphere here, we didn't treat this as a solid of revolution. So, you know, the first example wasn't a solid of revolution, just to point that out, but the rest were. Figure 12 shows a solid with a circular base of radius 1. Parallel cross sections perpendicular to the base are equilateral triangles. Find the volume of the solid. Okay, so the idea here is that you've got these equilateral triangle cross sections. The cross section with respect, if you have a plane parallel to y, each cross section is an equilateral triangle. The size of that equilateral triangle is based on so you know the base is a circle. So it's based on you know your position x, and you know your position on the circle. So like this here, we look at the circle, this is, at this point, this is the base of the equilateral triangle. So it has every side length of the triangle is this length. Okay, and so again, if we're trying to find the volume of a solid based on what we've learned in this section, how do you set that up? No matter what the problem is, right? This seems like a different problem, so it's like, well, you're kind of lost, and how do you work this? No, it's the same idea. We need to find a as a function of x. So we're going to put this piece oriented like this, with the x-axis coming out here, y-axis coming out here. Okay, with that orientation, what is a as a function of x? The area, the cross section as a function of x. Well, for any position x, you can get a formula for the length of this line. And then with the length of that line, you just use the area of an equilateral triangle formula. So you can easily get a of x. Then you just do a of x delta x. That's the differential piece. Integrate it. Okay, they give another example here of a pyramid, finding the volume of a pyramid. You know, this is easy, right? You have to get a formula for the side length of a cross-sectional square that cuts through the pyramid at each position x. Get your differential element and then integrate it. So we'll work a bunch of examples like this. Okay, so here it says a wedge is cut out of a circular cylinder of radius 4 by 2 planes. Yeah, so we're going to work a bunch of examples. You're just analyzing the problem. If you're trying to find a volume, as far as what we learned in this section, you're trying to find that a as a function of an independent variable, the area of the cross section as a function of the independent variable, all along the length of what you're trying to find, then integrate it. So in this video, the concept of how to find volume via integration, the volume of any kind of solid or solid piece via integration should be clear to you. And it should be clear that, every problem could be unique as far as you have to kind of look at the problem from different angles to see, okay, what's the situation? Okay, what's the, how am I finding that area as a function of x here? And then what's going to be the delta x? And so you set it up to where it's clear that, okay, I can definitely see I know the volume I'm looking to solve for, right? In here, you're trying to solve for this like piece cut out here, the volume of that piece. And I've clearly have it set up to where as a function of any x along the volume cross section, I've got a formula for the area of that cross section, and then I can multiply that times delta x, and so I can have a formula for the volume of a little piece, of a right cylinder piece within the cross section at any point along that volume, so I can integrate it. So let's work some examples.